Design of a tall building structure is a challenging field which requires some extensive calculation and advanced analysis. Due to its height, any tall building is subjected to large force components, and as the ratio of overall height to the base area is significantly high, structural stability due to lateral force is also compromised. To resist any gravity or lateral load without any significant structural damage, several advanced structural elements are introduced in a tall structure like shear core, belt truss, or outrigger elements. Also, advanced analysis considering all possible conditions is performed, like dynamic analysis along with second order p-delta analysis. Do you know how easily we can handle all these requirements and design a tall structure using RAM structural system? Hi, my name is Surajit Ghosh, and in this video, I'll give an overview of tall building analysis using RAM structural. I will discuss about the effects of different lateral loads, including wind and seismic load on a tall building, how to perform dynamic analysis along with second order p-delta analysis, and selection of proper method for eigensolution. Also, I'll cover few important aspects like construction stage analysis and drift control, which plays a vital role for any tall structure. Though I am not going to cover the structural element selection and modeling of shear core or basement wall in this video, still I want to mention few key points about this structure. This is a 46-story building with 2-level basement and 3-story podium. For basement walls along the periphery of the structure, finite element mesh is used. Modeling in RAM structural is based on physical modeling approach, so all the meshing is done internally. We need to specify the boundary only. Similarly, the shear core and float diaphragms are modeled using finite element, and as the mesh is generated internally, there is no improper beam or plate connectivity problem. To generate this model, I have created several floor plans as you can see here, like different plans for foundation, podium, and typical floor level, and these plans are assigned to relevant story which is used to generate this 3D structural model. At the roof level, a composite deck is assigned with steel beams and joist. I-section is used as the supporting column. Also, a dual framing system is used with separate gravity and lateral framing system. This is one of the major advantage of RAM structural. We can specify members as a gravity or lateral member and distribute forces accordingly. Finally, I have specified all the floors as rigid floor diaphragm. RAM structural has 4 different types of diaphragm like rigid, semi-rigid, flexible and pseudo-flexible, and we can select the diaphragm type as per the structural requirements. Well, I am not going to discuss about this framing and modeling options as this will require a detailed discussion. For this session, I'll focus only on lateral load application and analysis part which plays a crucial role for any tall structure design. Most of the time, lateral loads govern the reinforcement and structural element selection and placement. First, I want to discuss about wind load. We know that wind load varies with height. Near ground, wind force is opposed by the surface friction and also due to the presence of multiple obstacles, including other structures. But as the height increases, wind gradient changes rapidly. If we consider any international design code for wind pressure calculation like AC 716 or IS 875 Part 3 code, we can find that wind pressure intensity directly varies with the height from the base level. So if the structure height increases, the top floors will experience more force due to increased wind intensity. There are several other factors which governs the wind pressure, like the terrain category where the structure is located, or the topography and cyclonic importance factor. Specifically for any tall building structure, there are several other criteria which is required to compute the applied wind intensity value. One of these is the interference factor. For Indian code or IS 875 Part 3 code, it is mentioned in clause 8.3. For any tall structure, you need to find out the interference of wind due to the presence of other building structure located in the catchment area or the nearby zone. Depending on the dimension of the building, the interference area is determined, and further, depending on the height of other buildings, the interference factor is computed, which determines the final wind load intensity value on the tall structure. In general, we consider wind load as a static load applied on the cladding or directly on the members and does not compute the dynamic effect. But for any tall structure, it is very much required to include the dynamic effect of wind along with the vortex setting effect. When wind force is applied on the structure from a direction, along with the direct pressure load on projected area, we need to consider the cross wind effects and drag forces in other part of the building. I'm not going too much technical details due to time restraint, but all these effects needs to be computed for wind analysis, and if the effect of wind is much more significant, then it might be required to change the shape of the building to more aerodynamically sustainable shape, like Burj Khalifa. To capture all these wind effects on a tall structure, a detailed analysis is required, which can be achieved using wind tunnel test method. In wind tunnel test, a scaled model of the actual structure is created along with other obstacles and buildings present in the nearby catchment area. The scale factor of the miniature model depends on several criteria. And finally, scaled wind force is applied on this miniature model and structural response is recorded. For any tall structure, this wind tunnel test is a must, where we can predict the actual structural response to the wind load, not only for the regular wind load, but also for any moderate cyclonic effect on the structure. Each international wind code suggests this for a tall structure. For example, in Chapter 31 of ASC 716 code, wind tunnel test procedure are described which must be followed for wind analysis of any tall structure. In RAM structural, this wind load can be automated. There are several options to apply wind load. First one is the static or dynamic wind load using pressure coefficient method. Different international code like AC7, Eurocode, Australian and Canadian code, along with Indian code are implemented in RAM. This is just a one-click operation, so you can simply select the design code and provide the inputs like the terrain category, basic wind speed, wind direction. Depending on these inputs, program first performs the eigensolution to find out the mode shapes, and depending on the mode shape, as per the codal specification, it distributes the wind load intensity in all possible directions. No need to provide same data again and again to generate wind from different direction. If you perform wind tunnel test, you can directly import the test data using the wind tunnel option. This is a great feature where you don't have to analyze and modify the wind tunnel test results manually and feed the program height versus intensity values. Rather, you can only provide the story forces in the form of lateral load and moment about vertical axis. Also, percentage distribution factor can be specified, which is used to combine the wind load cases or cross-directional wind effects. All these values are generated directly from the wind tunnel test, and you can simply copy-paste the values in these tables. Program internally analyze the data and apply the wind load on the structure at the specified XY coordinate. There is another option where you can provide the wind load as a story force, depending on whether you have assigned the rigid or semi-rigid diaphragm. This is used only for some specific cases. Now coming to the seismic load application. Tall structures are more vulnerable to earthquake. Seismic force, base shear and story shear values are proportional to the mass of the structure, and for any tall building, overall gravity load or seismic weight is considerably very high, which increase the seismic vulnerability. It is always a challenge to minimize the seismic effect. If any tall structure is located in high seismic prone area, we need to take additional steps to minimize the seismic effect on the building, like installation of base isolation system or inclusion of tuned mass or liquid damper, which significantly reduce the earthquake shaking of the building. In Taipei 101, a massive tuned mass damper is installed, which helps to reduce the moderate earthquake effect. Also, it is a challenge for the structural engineer to select and place the lateral load resisting frames, including shear walls, bracing system, outrigger elements properly so that not only the seismic force is distributed properly, also additional torsion due to static eccentricity is within limit. If we consider any seismic code like AC 716 or IS 1893 2016, dynamic analysis is a must for tall structure. We need to perform response spectral analysis or time history analysis with ground motion data to find the relevant mode shapes and response quantities for each mode. And finally, combine the individual modal results using any modal combination method like CQC or SRSS to get the final response quantity. That is the basic of dynamic analysis. In RAM structural, there are multiple options available for seismic analysis. First one is the static seismic analysis. Like wind load, there is also a single click load generation option available where you can simply select the code, and depending on the selected code, the input parameters are available. All standard inputs are required like the R value, which equation is used to calculate the time period, soil type. Inputs needs to be provided single time for both direction, and orthogonal effects can be considered here. In several codes like AC7 or Indian code, it is mentioned that effect of 100% load from the applied direction along with 30% load from orthogonal direction needs to be considered. If you select this option, program computes the orthogonal load effects. No need to combine the loads using load combination method. This method is more accurate as during analysis, seismic load is properly applied from both directions. Also, accidental eccentricity value can be considered in both directions with same or different factor. As diaphragm is already specified, inherent torsion due to static eccentricity, which is the difference between the center of mass and center of rigidity, is already considered in the analysis. Similarly, you can create response spectral loads by selecting the code and providing proper inputs like the scale factor and eccentricity direction. Program computes the signed response quantities considering the sign of the dominant mode. Static seismic analysis is not actually required for tall structure, but few codes suggest to compare the base shear values obtained from dynamic analysis with that of static analysis. So it is always suggested to provide the static seismic load along with the dynamic load, and ratio of the base shear needs to be specified as a scale factor. Seismic mass required for the analysis is auto-calculated by the program from the gravity load. You have already defined the dead and live load during modeling, and no further input is required to define the seismic weight. But if you want, you can manually modify the seismic weight from the mass option. The center of mass of each diaphragm is also auto-calculated from floor geometry and mass model and reported here, which can also be modified. And if you want to consider the reduced section properties for seismic analysis, that can be done using the crack section property information during property assignment. During dynamic analysis, program computes the mass participation factor for each mode, and if cumulative mass participation factor is well below the prescribed limit in the code, like 90% for IS 1893 code, then program go for higher modes. Now, if there is any smaller structure present in the tall building, like an antenna or a tower on the roof, that contributes significantly when the structure is oscillated due to earthquake. There might be several hundred local modes for which only these isolated structures participate, and participation of the rest of the structure is insignificant. This eventually increases the number of modes considered. As you can easily understand, this local modes does not contribute anything to the overall mass participation if the main building remains idle. So overall analysis time increases due to consideration of higher number of modes. To minimize this, there are multiple eigenvalue analysis methods provided in RAM structural. By default, subspace iteration method is used for eigensolution. But if you end up with a situation where local modes govern, then you can use more advanced eigenvalue analysis approach, which is load-dependent ridge vector. The main benefit of this method is ridge vector ignore modes that do not contribute to the response of the structure in the direction of interest. So it requires fewer modes to get to desired mass participation. For subspace iteration, you may find that first 100 modes are local modes and it might require 200 modes to get 90% mass participation. Whereas this method requires 100 to get the same mass participation ignoring the local modes. Along with that, ridge vector method is faster and requires less memory than a dynamic analysis using traditional eigensolution. So overall analysis time is reduced, and for tall structure, the difference is several hours. Coming to the analysis process selection, for any tall structure, first order elastic analysis is not sufficient, and we need to consider the second order effects where the deformed shape of the structure is considered. P delta analysis is one of the second order analysis which is implemented in RAM. Just some background information. P delta analysis is an iterative analysis which is mostly used for building structure. For this method, force vector is modified at each iteration without changing the stiffness matrix. Initial deformed shape due to the applied load is calculated, which is termed as delta, and then the load is applied again on the deformed structure to compute the additional moment value generated due to the deformation, and this process continues till the stability is achieved. For any tall structure, this additional second order moment value is reasonably high and must be considered during analysis. You can simply switch on the P delta analysis option in RAM, considering the mass either from the mass model or from factored gravity load. Now, I have also mentioned that dynamic analysis is required for tall structure. So we are actually combining the result of two iterative analysis, which is in general not possible. RAM structural is capable of handling dynamic analysis along with second order analysis like P delta. This is performed using the geometric stiffness matrix or the KG matrix. This is an alternate procedure to capture the P delta effect in the analysis by combining the global stiffness matrix or K matrix with the global geometric stiffness matrix, forming a new matrix called K plus KG matrix. For this, only two steps are performed by the program. First, the deflection is computed from linear static analysis, and then the axial force values are calculated, which is further used to form the geometric stiffness matrix. With modified stiffness matrix, it is possible to combine dynamic load case along with the P delta analysis results. Apart from this, RAM structural has a very powerful analysis engine. For any tall structure, there are several thousand members along with finite element mesh. With dynamic at P delta analysis, the analysis process is very complex, and if the analysis engine is not powerful, then it might take several days to complete the analysis. RAM analysis engine is considerably fast, and you can select the solver as per your requirement to further optimize the analysis time. Not only that, it can utilize the full capacity of your system by selecting all available codes. So if you have a high-end machine, you can utilize the full capacity of the processor, and this will significantly decrease the analysis time. And finally, analysis in RAM structural depends on the selected load case. This helps a lot to minimize the analysis time. After analysis, if you modify something in a particular load case, you can only select that load and analyze. No need to reanalyze all load cases. Say you have modified the wind load and during analysis, you can simply select wind load cases and analyze. You can skip the analysis of seismic or gravity load cases as these load cases have already been analyzed and results are available. Reducing the load cases in each analysis stage decreases the overall analysis time. When we analyze any structure using a structural software, we create the stick model with proper location of the structural elements and provide the property values which are used to compute the stiffness matrix. During analysis, we consider the maximum amount of load that can be subjected to the structure. For gravity load, we apply all types of loads in each float simultaneously. Means we assume that all the dead and live loads are acting in all floats at the same time. This loading condition is valid for a completed building with full capacity residents. If you consider the construction phase, then this structural model is not correct. In reality, it takes several years to complete the construction of any tall structure, and consideration of full load on all floors does not replicate the construction stage loading condition. There are several structural aspects like material property change, creep and sinkage deformation, which are directly related to this construction and loading phase. And effect of this on structural behavior must be considered properly during analysis. These effects might be very small for any small structure, but for any tall building, the effect of time-dependent loading are moderately high. So construction stage analysis needs to be considered in analysis for any tall structure, which considers change in geometry, material, and loads during different phase of construction. Consider this building structure. This is a multi-tower building with podium level for commercial utility. You may have noticed for any building project, whether that is a single tower structure or multi-tower connected basement structure like this, all the towers are not constructed at the same time and also not in same pace. Some portion of the structure is constructed first and then construction work starts at different part. This rotational construction process goes on. I have tried to replicate the construction stage of this building, how different floors are constructed at different time. This whole phase of construction with differential load application needs to be analyzed properly. For example, take a portal frame from any building structure. As per our normal analysis method, we apply all load on all floors and analyze the structure. In construction phase, each floor requires considerable amount of time to complete and then the next floor is constructed. These are the construction phase for each floor, and in each stage, loads are applied gradually, floor by floor, depending on the floor casting. And this can be represented like this. Also, you can notice that lower level floors are loaded for more duration than the upper level floors, which generates differential deformation. In short, this is the basic of construction stage. Now, the question is why we need to consider this phased analysis. And the reason is to consider the effect of sequential load application on the structural behavior and to consider the creep and sinkage related deformation along with change of concrete modulus over time. The last part is termed as time-dependent effects. Creep is related to the deformation of concrete members over considerable length of time under persistent loads. All concrete members starts to deform over time due to the applied load, and the deformation varies with time. Similarly, shrinkage is related to the volumetric change in concrete members due to loss of moisture content. Concrete property also change with time as it hardens. Concrete takes time to gain strength and compressive strength increase over time. All this is considered in the construction stage analysis where creep and shrinkage deformation is calculated for each stage depending on the time and equivalent load is applied on the members. In RAM structural, construction stage analysis can be performed with proper inputs. We can directly specify the stage of each phase. in which order a floor is constructed. This can be automated also. Program assumes that the lower floors are constructed first and then the upper floors. Construction duration can also be specified. How much time is required to construct the floor, and accordingly program calculates the time dependent deformation. Three different types of material models are available by default, which basically governs the creep and shrinkage related information. When the formwork removed, when curing start, what type of curing method is used. Model B3 or Bazan-Baweja B3 model is one of the mostly used concrete model. Stage number can also be assigned to individual member or floor. It might happen some portion of a floor is constructed at later stage, like a beam or like a portion of the floor, not during the floor casting. And finally, construction stage load can be applied. Either you can consider only sequential load application, or you can also consider the creep and shrinkage deformation in the analysis, depending on selected material model. Also, you can replace the dead load results with construction stage analysis results, which is much more accurate. Just a comparison. First one is for deformation under dead load for regular and construction stage analysis. You can find a clear change in deformation values and pattern for stage analysis as time-dependent effects are considered properly. Second one is with the analysis results. Here also you can notice moment and shear values are considerably different for stage analysis. RAM Structural has a very powerful engine which can capture this sequential analysis properly, which is required for any tall structure. There is another aspect which needs to be considered for any tall structure, which is drift. If you consider any tall building, drift due to lateral load at top floors is quite high, and the whole structure moves back and forth due to wind or seismic load. Sometimes the drift is as high as 3 to 4 feet at top level floors. This drift can cause several problems and hence need to be considered during analysis stage. First of all, higher drift can cause serious structural damage if not considered properly in the design stage. If a floor shifts horizontally and columns are not designed to resist that movement, then obviously crack generates, and in severe condition, structural collapse. Another important aspect is the protection of non-structural elements like glass or partition walls. Almost all the tall buildings are covered with glass in the outer surface to resist the weathering effects as well as to maintain proper internal condition. For drift and column shortening effects, crack generates in the non-structural elements, which cause severe damage to the structure and dwellers. Also, higher drift causes discomfort to the dwellers. You may experience a motion sickness if the building continuously oscillates due to high wind force or seismic activity. So, drift control is very much necessary for any tall structure, and this can be done by properly understanding the drift behavior, by identifying the structural elements that can control the drift. Drift is different from deflection. Deflection is the distance of the old and new position of a node or member under applied load, whereas drift is the difference of displacement of a node at one story and displacement of the same node of the story below. So it is the relative displacement of two stories. There are several guidelines mentioned in wind and seismic codes as well as in the steel and concrete design codes to minimize the drift effects. For example, in AC 716 code in chapter 11 to 23, drift guidelines are mentioned for seismic load, and in chapter 26 to 31 for wind load. We need to consider all this for analysis. RAM Structural has a separate module which can perform the drift control analysis. Based on Castigliano's energy theorem or the virtual work methodology, this module can be used to identify those parts of the structure which is most influential to control the drift. It identifies which member is most crucial to minimize the lateral drift by increasing the stiffness of the member. Overall drift can be minimized by changing the stiffness of crucial members, either by increasing the area or by changing the I value. It can also identify the members, the size of which can be reduced without increasing the drift. You can create virtual workloads by specifying a nominal load at the concerned diaphragm level. Normally, the load is applied perpendicular to the floor, but you can also apply the load with an angle. This virtual load needs to be paired with actual lateral load component. In the drift mode, this pairing can be done where the actual lateral load, like a seismic load case, is added with the created virtual load. Drift can be checked in one direction at a time, so only a single lateral load is selected from a particular direction and then perform the drift analysis for that floor. From the analysis results, you can easily identify which members are most critical for drift of that floor. All lateral members are considered in the drift analysis, and you can notice the color coding with critical member information. You can further check the participation of the concerned member depending on the axial, shear, flexural, and torsion behavior. For example, in this case, the flexural participation is more, so you can change the property value and increase the inertia value, which will reduce the drift. From drift analysis, you can get a clear identification of the participation of the members and accordingly can control the amount of drift. After analysis, we can use the results for member or slab design. Like we can perform concrete beam, column or shear wall design either using the inbuilt design engine of RAM or use integrated RCDC module. For slab design, we can use RAM concept module, which can use the finite element results for RCC or post-tension slab design. We can easily transfer the model along with the load to RAM concept. All selected elements like beam, column, and shear wall from top and bottom level are transferred here. We can further design the slab as RCC or post-tension slab. This will be covered later. This is just an overview. If you want to know more about tall structure design, let me know in the comments. And thanks for watching.